And we have to apologize that Dr. Fred Mendyke couldn't make it today because of the snowstorm that hit the upper part of Michigan. But our own Dr. Councilman has said to step in and share with us some of the more exciting and fun experiments from his YouTube channel, which you should all look at and check out because he has some really fun experiments on there. So I will hand it over to Dr. Councilman.
Thanks everybody for coming out. Today I'm going to describe to you some of the experiments that I've got on my YouTube channel. This started maybe, I don't know, maybe 4 years ago or so. I've always sort of wanted to capture the beauty of some of the things that I see when I'm doing experiments here at Spring Arbor University. And I'm very interested in getting connected with, say, art students or video students who enjoy capturing the beauty of the things that they see. I'm just a hack. Okay, I just film what I see, and I try to capture it in a way that looks interesting to me. But I think that with the help of, some students who knew a little more of how to capture beauty in video or in film, I might be able to do a heck of a lot better job. But these are just a couple examples of some of the various videos that I have on the channel. And I've learned a lot. If you go back and look at my earlier stuff, it's pretty bad. It's still not very good, but I've learned how to do some editing to help me along the way. I think that's a recent one. Of course, Coke and Mentos. That's a Mentos in a clear soda. I'm fixing the color there for everybody. So it's green color in the middle. And then this is a teacher catching this when I was at one of my school presentations. It was kind of fun. Kids had a good time too. So all I'm going to do is I think I've got 3 or 4, maybe 5 different videos that I'm going to show you. Some of them, like this one, they don't have a whole lot of views, but this is actually one of my most favorite experiments that I was able to do. I wish I could do this experiment live for you. I wish I could do it live, but I only found out on Wednesday that I'd be doing this presentation, so I didn't have enough time to actually buy some diamonds. So this particular experiment, what one does is one tries. Now those are diamonds that I bought for $50. So I was able to buy a bunch of diamonds of low quality, and I'm making use of the fact that diamonds made of doing that. Diamond is made of carbon, and you can react that with oxygen in the atmosphere to make carbon dioxide. Of course, you got to heat the snot out of it. And you might notice, I think at the beginning, was it 14.6 milligrams was the mass of the diamond, and after burning it in air, it dropped to 10.3 for a difference of 4.3 milligrams, which means that some of the diamond was converted to carbon dioxide, and we all have probably breathed in some of that carbon dioxide that I formed in the lab a little while ago. So this, over here on the right, that's a test tube that's filled with liquid oxygen. And I only was successful with this one time, and luckily I had the camera going. I'm heating the diamond, and I'm going to drop it into the liquid oxygen. Yes.
And your life insurance is paid up.
And that's what it looks like. Only successful once, but I caught it on video.
Wow. Wow.
And fortunately, I didn't scream with glee when this happened. Now this, what I'm doing here is I'm just pouring out the liquid oxygen that's left over to show that the diamond is gone. It has been converted to carbon dioxide that has now entered our atmosphere. And maybe it's going into a plant somewhere to make a little bit of sugar. Perhaps. Maybe it'll eat one of those sugar molecules that the plant has produced, and it'll become part of your body. Yeah. Kind of interesting. This second video that I'd like to show you is doing fairly well. I got connected with a chemistry and community college teacher down in over in Colorado. I get to go to conferences and meet other chemical educators that are goofy like me and like to do a bunch of different experiments. And I mentioned to him how I noticed when I went to Colorado and I did the Coke and Mentos experiment, the fountain tended to go a little higher.
It fell flat?
And I wondered if the reason why it went a little higher was because of the lower pressure that existed in the higher altitude where I was in Colorado, or I wondered if it was just because the bottles are pressured at a different, are bottled at a different pressure in Colorado than they are here in Michigan as a result of, difference in air pressure. So we decided to test this. That's Ryan Johnson there. And what we decided to do is we decided that I was going to send him some bottles bought here in Michigan, and I would keep 2 of them here, back here in Spring Arbor. The altitude here in Spring Arbor is about 1,000 feet. And he started at the base of Pikes Peak, that's the stuff I sent him. And he climbed up the mountain. This is some of you may have used this. It's the contractor we use to measure the foam volume that was produced. And this is Ryan at 6,800 feet at the base of the mountain where he started to climb. And you can see the various elevations where he tested everything. We're going through this really fast. And the various foam volumes. It's about 8,000 feet, 800 mils foam volume. It's jumping around quite a bit. We think we're having trouble controlling the temperature of the bottles, which is going to be important. I'm actually thinking of driving to the top of Pikes Peak sometime this summer and trying this myself.
Road trip for sure, for chemistry.
But we do tend to notice that foam volume does tend to get higher as you go up in altitude. 13,000 feet. Woo, look at that.
Wow.
Getting up there. Really getting up there. I think that was the best one, and at the summit it didn't go quite as high. I think it went to about 1,500 mils at the summit. And then here's me in the controls. We were posting this on Twitter as it was happening, and we had quite a following actually. It was kind of fun. And I couldn't believe what I saw. It was only 650 mils, so of course I ran it twice. And here's the data. It's jagged, but it sure does seem like there's a trend. Now, of course, I went back through, the idea is probably you can use the ideal gas law, or the combined gas law, and you can probably see, okay, if it's going to produce 650 mils of gas volume, if that same volume of gas was produced at a lower pressure, what would the volume go up to? And so we've corrected those data that you saw for the ideal gas law. And it turns out that correction is not enough to describe the increase. So something other than just expansion of gases at lower pressures is going on. And there's a researcher over in France who does a lot of work with champagne bubbles, who claims that champagne degasses more quickly under lower pressure. So that's probably what's going on with that, I'm guessing. This happens to be my most popular video. This one hit 1 million views. I think it was about 2 months ago, and we're getting close to 1 million, and we're getting close to 2 million here pretty soon. We'll see. But anyway, this video I'm just putting my hand in liquid nitrogen, and I'm describing why when you put your hand into liquid nitrogen, it doesn't hurt you. And the reason why you can, I'll just show you here. I mean, might as well do it for you. Here's my goggles. So in this bucket here, I have some liquid nitrogen right here, and you just take your hand, you can just stick it in and take it out real fast, as long as you don't leave it in there for a real long time. So I got a little bit of mine soaked into my shirt. That's not good. Just want to move it away from my skin.
Frostbite.
There we go. So what is going on? Why can I take my hand and place it into something that is minus 321 degrees below zero on the Fahrenheit scale? Negative 321, I just put my hand in it. It's not bothering me at all. Why is that? Why can you do that? Well, it has to do with this effect here called the Leidenfrost effect. And we're going to describe the Leidenfrost effect with water first. If you've ever been ready to cook and you decided to sprinkle a little bit of water on the pan prior to cooking to see if the water kind of beaded up and sizzled around and maybe moved around the pan, you're making use of the Leidenfrost effect. You're making sure that your pan is hot enough for cooking because the water doesn't boil away real quickly. And the Leidenfrost effect just basically says, if a liquid contacts a surface that is much, much higher than the boiling point of the liquid, then a vapor layer forms that insulates the liquid from the hot surface. So we're looking at this, if we've got if you've got water droplet on a warm surface, it's going to evaporate quite easily. If it's just above boiling, you'll see some slow boiling. As you continue to increase the temperature, you may get to violent boiling, and then at some point, when you even increase the temperature further, what happens is that the water pretty much doesn't boil at all. And what's happening there is it's boiling so fast that it forms a little vapor cloud, and that's sort of represented by the little cloud beneath the blue oval. That vapor cloud, the droplet rides on the vapor cloud, a lot like an air hockey puck rides across an air hockey table on the air vapor that's blown up from the table. And they have these things called a Leidenfrost temperature. The Leidenfrost temperature for water depends on a lot of different factors, including the surface upon which the water is placed. But it roughly runs about 200 degrees Celsius, which is almost 400 degrees Fahrenheit, roughly speaking. So this is a video of droplets on a surface that is undergoing violent boiling. The surface is hot enough to make the water boil, but as you can see, the water boils away rather quickly as soon as the drop is added. It's a hot surface. Notice 150 C, 300 degrees Fahrenheit. Now we're going to do the same trick, but in this case, we're much hotter.
Oh, wow.
It is cool. And you'll notice when the water flattens out and makes contact with the surface, that's when you sort of see some of the boiling take place, or at least some energy take place. In this case, on this surface, there's some hatches, so the surface has been made so that there are jagged edges like this. And this has been heated to a very high temperature, and what happens here is when the droplet hits this surface, the vapor that's produced pushes it to the next hatch. And it pushes it to the next hatch, and you can actually direct where the droplet's going to go. And if you look online, there's some people who have done this, where they've made a maze. And they'll stick a droplet at the starting point that moves through the maze based on the hatches that they placed in there. I want to show you this particular experiment. This is kind of fun. Show you the Leidenfrost effect here with this. I'm going to take a little bit of water.
How come every councilman thing always involves fire? That's an excellent question. That's true.
And I'm going to heat this brass sphere. I'm going to get it kind of hot. Hold it over there in case it melts off. That's happened to me before. It's about there. I'm going to place it in the water. And it hisses. Right? Now I'm going to heat it to glowing. It's going to take a little while.
Do you have to turn it around, or does it? Rotisserie part is kind of more expensive. I just wonder how fast it goes. What makes it fall off? Is it liquefied?
Not yet.
glowing hot. I'll place it in the water. Took a little longer, didn't it?
Yeah, it did.
Yeah? It didn't go quite as fast. Now what's going on here, I'll show you with the next video. So this is a video of, a slow-mo video of what I just did, focusing in on the sphere. You can see a vapor layer that surrounds the sphere that collapses later. So again, what's happening here is when the sphere is inserted in the water, it's so hot that the water that contacts it boils extremely fast, and it forms a vapor barrier around the sphere, and that vapor barrier protects the sphere from the water so that the energy doesn't go from the sphere to the water. It's thermally insulated until it cools enough, and then once it cools enough, the water, when it gets near the surface, can't boil away quick enough to form the vapor layer, and then it collapses in as you saw.
Does that have to do with the surface tension of the water?
Certainly, yeah. I'm sure that plays a role. I haven't done experiments, say, with alcohol. I imagine it would look a little different.
Or gasoline? Yeah, like it's
Right.
I don't recommend that.
So as you saw, liquid nitrogen, now we're going to sort of think about this a little differently. We've been thinking about the Leidenfrost effect in terms of water. And since we're made of water, you know, we think of things that are hot as things like 400 degrees Fahrenheit, an oven, or the coils in a toaster. If, for example, we were made, we were liquid nitrogen-based life sources, and that was the fluid that was used in our bodies, what we would be experiencing right now would seem like an oven. In fact, much hotter than an oven.
Yeah.
Because the temperature that liquid nitrogen boils at is minus 321 degrees Fahrenheit. And we're 400 degrees Fahrenheit above that right now, roughly speaking, in this room. So when nitrogen hits a surface, when liquid nitrogen hits a surface at 68 degrees Fahrenheit,
Oh, yeah. Okay.
it looks a lot like water on a hot stove.
Yeah, sure does.
And of course, I kind of wanted to push this a little bit, so I did it when the water or the temperature was really cold outside. So this is just in front of the science building at minus 18 Fahrenheit. We're seeing the same kind of behavior.
When was that? A couple of
Was that in January? When was it minus 18? It got pretty cold here. Was it January? Okay, I can go back and look and see. So even negative 18 Fahrenheit is stinking hot. That's a scientific term. Negative 18 Fahrenheit is stinking hot to liquid nitrogen. So when I take my hand and I place it, which is at, what's that, 98.6 degrees Fahrenheit, and I put it in liquid nitrogen,
Don't do that.
a vapor barrier forms around my hand that insulates it and protects it with the Leidenfrost effect. And you can see this in slow motion. If you watch carefully, the lighting's a little bad in here, but if you watch carefully, you can see the vapor barrier that goes around my hand when we dip it in slow-mo. It looks blurry, but those are bubbles that are around my hand that are insulating it from the nitrogen. If anyone would like to try this after the presentation, you're welcome to. You see how quickly I did it. You stick your hand in, you take it out really fast. And what's really interesting is that your hand is completely dry when you're done after sticking it into a liquid.
How do you know beforehand what kind of time it takes? I mean, there's a time element in there. How do you know if it's a half a second or a millisecond?
I saw someone else do this before I did.
There it is.
You don't.
There it is.
Okay, the last experiment that I'm going to go through, I don't know how long this is going to take me. Talking about this particular experiment takes a little while. So what I'd like to show you here is some of these blue butterfly wings.
We're going biology now. Okay, hang on.
Right, Chuck?
It was in J10.
That is true.
That's right. This was an
But it's a
article
butterfly
in Med.
That's me.
I need your password, yeah.
Oh.
Of course, the computer shut down. So I have some butterfly wings up here, and these butterflies, they tend to live in South and Central America, in the rainforest. And when their wings are shut, like this, that's what you can see. But when they open them up, it is perhaps the most beautiful color
Yay. I love it.
that biology has ever produced. Amen.
It's not amazing.
I'll go ahead and
Amazing.
let you just take a look at those. You can compare the back and the front. And what's really interesting about these wings, most color that we observe comes from chemicals.
Organic chemicals.
My shirt is colored kind of green because there are dye molecules in my shirt that tend to absorb red light and tend to reflect green light. And so when white light that's got all the colors bounces off of this shirt, the reds get absorbed, the greens get reflected, and because the green is reflected, that's what you perceive. But the goofiest thing about these wings is when we go into the wings and you look for a blue molecule, you don't find it. So those things are brilliantly blue, and there's no blue in them, so to speak. There's no blue molecules in there. So what the heck is going on? Well, this has to do with physics rather than chemistry in this particular case. So on these wings, there are tiny structures called lamellae. And so this is going to be the surface of the wing here. And then there's these tree-like structures that project upwards. And then they have these little ridges on them. And they're called lamellae. And light interacts with these lamellae in a special way. And I'm going to try to describe that to you, but in order to describe how that works, there's three concepts I've got to get across to you. The first is refractive index. The second is surface tension. And the third is diffraction. So we're going to cover those three concepts here. So refractive index is this idea, the refractive index of a molecule or air or a mixture or something. What it basically says is how much slower does light travel through the substance versus a vacuum. I have up there air, but it should say versus a vacuum. And light travels just a little bit slower through air than it does through a vacuum. And really it has to go 1.00029. But basically it's pretty
Where's
much
water
the
on that?
same.
Where would water be on that?
Water is 1.3 if I remember correctly, 1.33. Okay? So and what happens is when light goes from one medium, like through air, versus another, like glass, the light bends a little bit. It changes its path. And when light changes its path, our eyes are able to perceive that. So this is, for example, why mirages happen. Okay, because you have a heated surface that might be giving up a little bit of moisture. And so what's happening is when the light passes through that area, it gets bent a little bit relative to the cooler air that may have a little less moisture in it. So all sorts of stuff we can see with this effect. This is kind of fun to show you this sort of in reverse. It turns out that corn oil or vegetable oil has a refractive index that's very close to that of the special glass that we use in the chemistry classes, which is borosilicate glass. Very close refractive indices. So I'm going to take this test tube here, which just has air in it, and I place it in here, and you can see the test tube. Because as the light passes through the corn oil and the glass, it hits some air, it gets bent, it gets reflected, and we can perceive that. But if I fill the test tube with oil,
It's going to disappear.
it might. Let's see if it does.
Oh, man. Somebody had too much coffee this morning. Only 1/2 a cup. Bruce, I'm cutting you off. We like chemistry, man. He didn't put it in.
I'm up close, I can just barely see it.
Wow.
Because the refractive indices are not perfectly the same. But it looks like a disappearing session.
If you're not geeked out right now, you shouldn't be in this building. I'm just saying.
Place that up there.
That's very fair.
Now, why does all this matter? Well, it matters because the lamellae, in between those ridges, there's air, which has a certain refractive index, about 1. The lamellae themselves have a refractive index of 1.56. So that means when the light interacts with those lamellae, the light can get bent and refracted, reflected in a certain way. All right? The second idea that we're going to need to understand is the idea of surface tension. And the way I think about surface tension is in the following way. If I have a liquid here, surface tension tells me how much energy it takes to make that liquid spread out over a certain area. We can see that, for those of you who follow units like I do, we can see that from the units of surface tension, which are joules per meter squared. I have them listed in millijoules per meter squared. Joules is energy, meter squared is area, so it's energy per area. So to follow the units, they often tell you they tell you what the properties of the measurement is that you're looking at. And we can see that water has a very high surface tension. Alcohol and chloroform have low surface tensions, whereas liquid nitrogen has a really low surface tension. And that's important to these butterfly wings for the following reason. Imagine I place a drop of water on top of these lamellae. In order for the water to penetrate down into these lamellae, it's got to spread out. It's got to spread out over all those little nooks and crannies. It's got to cover all that area.
Wait, why can't it just go down between the two of them? Why does it have to spread out to cover the whole thing?
What do you think, Aaron? Why doesn't it just drip all the way down through? I imagine it's got to penetrate through. Well, in order to get there, it's got to get through. It's got to penetrate. That's like a forest. Just like rain's got to hit the leaves before it hits the ground, I imagine it's roughly the same thing going on here. And so as it drips through, it's got to spread out and cover that entire area. So let's check this out with these wings here. I'm going to add a little bit of water to one of these wings. And get it off. There we go. Let's add a couple drops of water, see what happens.
Water, not liquid nitrogen.
Nitrogen will be next.
Why can't get it out?
The water heats up. In order for it to spread out over the wing, it's going to have to leak into all those little nooks and crannies, which is very difficult for water to do because water has a very high surface tension. If I do the same trick with, say, some liquid nitrogen, let's see a different effect.
If it's small enough, it won't ever get in there, boy. Well, I mean, if the sizes are too small, it won't ever get down. It's going to keep the water from going down there. What? I thought it was blue.
It's not showing up white on the whites.
I think it was green.
You see the greenish color? Let's try it like this. Just hold it up. You can see it this way.
Do you have the light on the lady behind?
That's blue.
How do you do that?
There's a switch on the top, on the other side.
Okay, yeah.
Does that help?
That helps a lot. There, it's green.
Oh, there's something else going on. Oh, wow, look at that. You can see it's blowing off. Let's see that. Watch it evaporate.
There, now we're seeing.
It's an interesting effect. There's something goofy going on there. We'll talk about what that might be that's going on. So the other idea that we need to discuss is diffraction, which is, it answers sort of the question, how does light behave when it passes through tiny openings? Diffraction means when a wave passes through an opening that's about the size of the wave, the light gets, or the wave, I should say, gets bent. I like to do this experiment when I'm talking about diffraction. Can you see me?
No, you're not there.
Can you hear me?
Yes.
Okay, sound waves are roughly feet in size, meters in size. And so when I spoke, and the sound waves were traveling through this opening, they didn't all just go straight this way and nobody heard me. They diffracted around here and you all could hear me. Now light waves are much tinier. I can't show you with my fingers how small they are. And so when I'm standing here and the light waves are going through this opening, they just keep heading straight in this direction. They don't bend around, you can't see. And it turns out that waves get bent depending upon the size of their wavelength. And I've indicated this here. You can see the red light gets bent more than the green, which gets bent more than the blue. And so what happens with these lamellae, there are structures on the lamellae. The lamellae itself has a thickness of about 54 nanometers. It's pretty tiny. That's about the size of light waves. Light waves are on the orders of hundreds of nanometers. And the gaps also have a certain distance between them, about 142 nanometers. And those are spread over the entire wing. There happens to be an equation that's been given that says you should be able to tell what is the wavelength of light that is most likely to be reflected off of the surface based on all of these parameters, where N1 is going to be the refractive index of the air gap, which N2 is going to be the distance between the air gap. M1 is the, refractive index of the air gap. D1 is the distance between the air gap. N2 is the refractive index of the lamellae itself. And then D2 is going to be the thickness of the lamellae itself. And what happens is you can't mess with much of this. I mean, I can't mess with the lamellae, so I can't change, the 54 nanometers, and I can't change its refractive index. I can't change the distance between the lamellae, but what I can do is I can take liquids that'll soak into the surface and change what's inside the air gap. I can change that from being air to other liquids. And when you do that, you actually get different values for the expected wavelength. And what's going on here,
Well, it says what changes the color.
and that's what changes the color. And what's going on here is when the light waves strike the surface, in the normal wing, all colors of light except for blue are destructively interfered with, and they cancel each other out. The blue wavelengths, those hit the surface, they are constructively interfered with, and those get reflected back into your eye. And that's why you get this brilliant blue color. Now, of course, I wanted to test out this particular equation. And so what I did is I just took a light and shined the light onto the surface of the wing. And then I collected the light that was being reflected back. And I did this after soaking the wing with various liquids. So with air, the expected wavelength is 452 nanometers. This is about what I found. So this is the light that was reflected off of the wing. And I'm not sure, look, I only did this, I spent like an hour in the lab doing this. So I'm not certain these numbers are right. I'm not certain that I got rid of all reflected light, like some light could just come in and just really just bounce off the surface from the light itself. I'm not certain I subtracted out the light from the source. So you should recognize that. But I am curious because I do see a mismatch between the positive equation and my observations. They're close, and you can see a shift. This is with liquid nitrogen. That one works pretty well.
Yeah, 509, yeah.
Isopropyl alcohol should be about 550. That one works fairly well also. And then chloroform should be 579. That one's not too bad either. But you also notice that there's quite a big spread. This wavelength should be the center wavelength. And there is a slight mismatch there, and I want to figure out what I'm doing wrong, first of all, in the analysis, but I also would like to, study this a little further. If anyone out there has some time, you'd like to fiddle around with butterfly wings.
If you desiccate the wing at all, does that change the, because with the air, I wonder if there's any water vapor that may be playing havoc. I wonder if you desiccate the wing first.
That's a good idea, yeah, I never thought of that, yeah. All right, that's all I got for you. Any questions, anybody has any?
Richard,
You mentioned that you use rather low quality diamonds. Do you think that there might have been impurities that affected that experiment?
The question is, I used low quality diamonds in the diamond burning experiment. Do you think there are impurities that would affect the experiment? I don't know, but it would be kind of expensive to test that out. Because the control is going to be expensive. What makes it low quality? I think the color, the cut, the clarity, there's some other stuff that you have to worry about. I missed one of the C's. Yeah, I missed one of them, but I'm just buying diamonds for $50 and trying to get the biggest ones that I can. That's a fun experiment. If anyone wants to try that, let's buy some diamonds and try it. It's fun to see that thing light up like a light bulb in some liquid oxygen. Other questions? Yeah.
Have you looked into any other insect wings or butterfly wings that have similar, like lamella, but refractive colors?
Dr. Baldwin, you want to answer that question?
Yeah, we've tried and failed spectacularly on beetles that seem to have a similar iridescent color. It happens to be green. I think the main problem, we can't do this demo with beetles, is we can't get the waxy coating off of the beetle's body. The carapace is coated in wax. And we've tried acetone, we've tried chloroform, we've tried methylene chloride. All the go-to solvents that organic chemistry has provided the world. Epic fail.
Can't get it off.
Can't get it off.
Wow.
Yet. Maybe there's an answer out
have
there.
you tried urea?
No, I haven't tried urea.
Because beetles, their exoskeleton is embedded with resin. Resin's a highly, you might, reducing agents might also, because there's lots of disulfide bonds.
Okay.
Wow. All right. Hadn't thought about that.
I did recently read, and I don't know if this is true or not, okay, but I didn't read the article carefully enough, but I did read that I think there's a blue tarantula. So if anyone wants to sort of, inform me on that, whether that's an actual thing or not, get out there and look around, see if that's a real thing. Well, if you want to stick your hand in liquid nitrogen, you're welcome to come on up and give it a shot. Just don't leave your hand in there too long.
No.